So it turns out, let's draw a quick picture. Let's draw a quick picture. In this case, here's 0, here's time t, here is this is half. We want half of that, so that's going to be here. So it's going to look like this. It's going to be exponential decreasing. Here is k0, here's kt. So the population, the length of time it takes for this is no longer, we know, because the population is shrinking, we don't call this, typically we don't call this a growth model. R is negative. We call this a decay model. So we call this exponential decay. And it turns out that we use this far more frequently than we look at the exponential growth model. It turns out that this log 2 divided by the growth rate gives you the exponential decay. That's something that we often refer to as the half-life. And the reason why it's more familiar is because we talk about radioactive decay. So we talk about radioactive isotopes and we talk about the half-life of radioactive isotopes. It turns out that this is exactly that calculation. It's the log 2 divided by the decay rate. And it tells you how many days or weeks or months or years or thousands of years for a radioactive isotope to decay until it is half as much mass of that particular isotope. Okay, so it turns out that doubling times and half-lives are exactly the same problem. Let's speed on to yet another problem. Now that we know how to calculate growth rates, I'm going to make a certain claim, and let's go back in time 10,000 years, and we take a look at rough approximations of the size of the human population at different periods of time. So it is approximated that around, let's see, the year here, and we'll talk about the global population here. And we think that roughly 10,000 years ago, around the year 8000 BC, we think that the global population was around roughly 5 million persons. We think that roughly 8,000 years later, around 1 AD, that the population was maybe around 250 million. That's 1/4 of a billion. The population around the year 1750, we think was around 3/4 of a billion, around 750 million. Let me just write down a couple more. Around the year, 200 years later, around the year 1950, we think the population was around 500 million. That's going to be 2.5 billion. We think that around the year 1975, 25 years later, the population of the global population was close to 4.1 billion. Let's see. I have two more numbers here for you. Around the year 2000, we think the population was around 6.1 billion, 6,100 million. And now, I should have looked this up, but around last year, we thought that there was around 7,700 million. So we could calculate what the R was between each of these periods. I'm just going to do it for the very first one. I'm going to say that that was 8,000 years roughly. So what we want is the log of 250 divided by 5. And we want to divide that whole thing by 8,000 years. And what we end up with is about 0.00, I think 3 zeros and a 5. So that is 1/20th of a percent. That's going to be 0.05% per year. Let me make a comment, and that is that if you plot the log of population across time, you don't get a straight line. We talked earlier about this diagnostic. It turns out that if you plot the log of population against time, it grows much faster. It's not linear. It grows much faster. So population has been growing faster than exponential. I guess I should say one more thing over here. You can do this thing. You can look at this. This is the R for the last 20 years. Should be something like the log of 7,700 divided by 6,100 divided by 20. And I think that thing is around roughly 1 1/4, a little bit more, a little bit larger than 1 1/4% per year. So we went from a 20th of a percent to 1.125%. In this last 20 years, so that is 25 times higher than over the first 8,000 years, from 8,000 BC up to 1 AD. You can verify that. Yeah, that might be a nice little thing for you to do.